pull up your lecture, pull up the spreadsheet, make sure that you have selected the Y products class, and we'll just practice entering the formulas in so that you're familiar with how you enter the sum product formulas in, because you'll need these for your homework. Anybody still pulling up the sheet? Okay. Also, any of you not here on Tuesday? Okay. So for those of you not here, once you open the sheet, let me know, because I will have to show you how to install solver on your machine, okay? The solver that's used for solving a problem. For Mac, the solver has to be, you can download it for free from Microsoft for Mac, and there's a link. So you just Google Microsoft, you just Google Frontline Solver for Mac, and you'll be able to get the add-in. It's an add-in, it's a separate thing. So, but now it might be something that you can do for the latest Office, okay? But just Google it and you should be able to find it. All right, so Christy, okay? All right, so those of you who were not here, go into File, and then go down to Options. Everybody here? File and Options. Okay, you're here?
File, Options.
And then, do you see the screen?
Yeah.
Okay, so the second last from the bottom, on the left-hand side, you have add-ins. Did you get it, Ty?
Yeah.
All right. So click on add-ins. And then once you're on the add-ins page, at the bottom here, you'll see Microsoft Manage Excel Add-ins. And next to that is a button, Go. So click on Go. And then you will see this dialog box. In this dialog box, all you have to do is make sure that you checked the solver add-in checkbox. Just check that one. You don't need anything else. So check the solver add-in checkbox. And once that's checked, then just say OK. And it should say installing solver and it will be installed.
So for Mac, you have to download that?
Yeah, so just say Frontline Solver for Microsoft and whatever your version of Excel is on, or Office on Microsoft, on the Mac is, okay? So everybody's with me so far? All right, now if you have formulas in these cells over here, make sure you delete them. Okay, so just highlight those cells and delete that. Okay, because you don't, that way you can practice how to add it in. Okay, so remember on Friday we stopped here where I talked about this is the objective function expression. Okay, so it's the sum product of the coefficients, and these red highlighted cells are my decision variables. Okay, so I'm going to use the sum product function, so it's equals to sum product, and the sum product has a number of entries, and you'll see these are arrays. Arrays are just groups of cells. In mathematics, you can think about them as vectors. Okay, so they're vectors or even matrices. And what I want to do is I want to highlight the decision variable cell. So you see this is highlighted, this whole row. Now I want to make sure that when I drag the formulas down, that I don't lose the reference to this cell. I anchor the reference here. Just like you saw in the homework, I showed you how to anchor it. So I'm going to press F4, and you see how it puts dollar signs around all the column and the row labels. So that means that that row is not going to change when you drag that formula down. Then to add the next row, I just put a comma there, and immediately you can see that I can enter another row in. So I then go in and I enter this row. So you see this row is equal in the number of cells to this row. It has to be. The dimensions of the rows, in other words, have to be the same. Same number of rows and columns. Okay? Those dimensions have to be the same. And once that's done, now I don't have to put any dollar signs around these, because when I drag it down, I want each one to change to the current row. All right, so that's it. Now I can drag this down here. And all the cells, all the formulas will be dragged down, as you can see. Okay? So this row stays the same, and then I have this row that is part of the sum product for that. So these are the actuals. This is the only thing that's different in Excel Solver. So I have the actual numbers over here. And just to refresh your memory, what the sum product is, so if I put a 1 in each one of these, I'm multiplying 1 and 6 and adding it to 1 and 5, so that becomes 11. Multiplying 1 and 3.8, so that becomes, and I'm adding it, so it's 14.8. And then multiplying 1 and 4 and adding it, and that's 18.8. Okay, so that's what the sum product is doing. It's just taking the product of the adjacent cells in the two rows and then adding all those products up. Okay? Yeah? So, now that is my sheet setup, and I explained to you that the Tableau is really something that is what you enter into here. Now, in order to solve the problem, or to set up the problem first, you go into the Data tab, and to the right here you'll see Solver. Now, if you are working in Mac, Solver will come up as a separate program that you have to call. Okay, so you will call the Solver program, and that's how you work. But here, Solver is built into this tab for data. You click on Solver, and you will get this dialog box. Okay? So, here, this is the objective cell, the objective function cell. This is our objective, minimum and maximum. We can also achieve a certain value. You can do a goal programming. But we're not going to get into that. All we are concerned with is minimum and maximum. Minimization, maximization. We want to maximize the profits, right? It's a production problem. By changing the variable cells, that's why I highlighted in red, because now I know those are my changing cells. Those are the decision variables. And then the constraints. So let's go in and do all of that. So that's my objective cell. I want to maximize, and my changing cells.
What's the objective cell again?
This is the objective cell, G6. Okay? That's why I like to highlight it. Once I click out of this. Now, the constraints. So, the constraints, to add the constraints, I just click Add. Okay? So, I click Add, and then, now see, the nice thing about this is all the constraints are less than or equals to. So, it makes it very simple. On the cell reference here, that's where Excel is different. I have to show that these are my actual values. Okay? So in other words, that's just the left-hand side function. Okay, that's the function that we write out, where the decision variables are the constraint is a function of the decision variables. Okay? So I can add all of those together because all of these constraints are the same. So I've added the constraints, or the left-hand side, and they're all less than or equal to. You can also apply an equals to, you can also apply greater than equal to, and we will look at integer, binary, and the difference. So this is less than or equal to, and that's the right-hand side. Now notice the right-hand side has got no decision variables, okay? So these are no decision variables over here. So once I've added my constraints, all I have to say is OK. Now, if I want to add other constraints, if some constraints are greater than, or some constraints are integers, so I have to set these values to integers, then I keep saying add, and then I go back to more constraints, and keep adding more constraints. Okay? So now that I've added all my constraints, I say, okay, it goes back here. Now, there are options. I can use a complex algorithm, I can use a nonlinear, or I can use the linear program. We're always working in linear programs, so always select the simplex algorithm, the simplex LP. Okay? Is that clear? We're always going to use simplex. Yes?
What's the variable cells again?
These are the variable cells.
Oh,
Okay? The red highlighted are the variable cells. So simplex LP is the algorithm we're going to choose. And there's a whole bunch of options here. You really don't have to worry about them. And as I said, the notes are a little bit outdated. I have to update them with the latest version of Excel Solver. This is a constraint precision. How precise you want your constraint to be met. How many decimal places. Don't worry about any of these other ones. What's the solving limits? These are usually used for nonlinear and large problems, which is not something that we're going to get into. Again, this is nonlinear, and these are the evolutionary or the genetic algorithm type problems that we're not going to solve. So we say, okay. And another thing is we're going to say that we want all of our decision variables to be non-negative. Okay? So remember the restrictions on our variables, non-negativity, this is where you state it. These are all non-negative restrictions. Okay? So once you've done that, then you can either close and it's all saved up. So what I'm going to do is I'm going to format this. So it looks, this then becomes the objective function, and these are the constraints. And now when I want to go back, I can always go back to the solver, and everything should be already set up for me. And then all I have to do is hit solve. And there I have the solution. Now, the solution was provided in a few milliseconds. So you'll get this dialog box and you'll say, you want to keep the solver solution, or you want to restore it to original values, and what reports do you want? So limits reports we're not going to be concerned about. We're not doing nonlinear or large programming. What we're going to ask for is we want to ask for the answer report and we want to ask for the sensitivity report. Okay, so those two reports we want. We can just click on them to highlight them, and then we can save the scenario if you want, but we won't get into that. And we can say OK, and then immediately you'll see the sensitivity report and the answer report. Okay? So what is our solution? Our solution is we should make 40,000 square feet of industrial cloth, 2,000 square feet or 20,000 square feet of insect screen for a total profit of $3,400. Okay? So that's the production problem. And that's all for you. So now you know how to solve a linear program. Okay? It's that simple. It is, really, once you get the hang of it. They're not paying you your 5-star salaries for no reason, you know that. All right. So, what do we, as a manager, are concerned about? Our customers don't only want us to produce industrial cloth insect screen. Might not be optimal, but we want to figure out what the problem is, right? So one thing that we could do is we could say, maybe if we increase our profit, maybe we increase how many resources we have. We don't really understand. How do we know what's going to affect that? And that's where the sensitivity report and the answer report is really, really helpful. Okay, so let's start by looking at the answer report. So the answer report gives you all kinds of cool stuff. First of all, now remember that this is a small program. Okay, it's got 4 decision variables, it's got 3 constraints, and that's it. But in reality, when you're doing a real problem, you'll have 30,000 constraints, you'll have 100,000 variables, you'll have a very large problem. And you can't see it all in one shot. So the answer report is really helpful in that respect. So you can see what the original value was. So if you input some heuristic values, for example, then you can see what the heuristic solution was, and you can see what the optimal solution was. And you can see what the heuristic or the objective. And you can see what the original solution was and what the final solution. Now here, this is the final solution. It tells you that these are all continuous variables. Okay? Now, these are the constraints, and some really interesting information over here. Now, there are two columns. This is the cell value that you've set, and this is information telling you binding or not binding and slack. So, it's binding. This tells you that it's binding because you've used up all of the resources, 6 and 10 of the machines. All right, so 600 hours and 1,000 hours of the machines is used up. So in other words, it's telling you that the maximization of the profit is restricted by this. There's no slack over here. So that's one clue. All right. So then that gives us an idea of where we need to look for in the sensitivity report. It's telling us that the amount of aluminum available is not a problem because we've got still 500 weight as slack. In other words, we've not used 500 weight. And that's pretty cool to know also, right? That means we don't need to go out and buy. The aluminum is not restricting the problem. But we know that there is 2 binding constraints. So let's go and look at those. So the sensitivity report. Now there's all kinds of cool stuff over here. So it tells us what our final value is. And then it tells us something very interesting over here. Something called a reduced cost in the next column. Now Excel is a little bit funky over here, so it's something that it's not intuitive, unfortunately. But when you think about maximization and minimization, then it makes sense. So what is a reduced cost? Reduced cost is the mathematical term based upon the theory. So just understand what this is. Reduced cost, now we want to maximize our profits. The value that we have right now for profit margin of roofing mesh is 3.8. Everybody agree with me on that? For each 10,000 square feet of roofing mesh that we sell, we make 3.8 or $3,800 in profit, right? Yep. What the problem is telling me, what the lean program is telling me, is that if I increase this profit margin from by 5.7 or by $5,700, then I'm going to start making roofing mesh. Right? So in other words, it's telling me I need a price increase in order to make that product profitably as an optimal solution to this problem. So I need to increase this price from 3.8 units per 10,000 square feet to now 9.5 units per square feet. Okay? Is everybody okay with me on that? Okay. And here it's telling me how much I can increase it by and how much I can decrease it by before the solution completely changes. And what is that solution? That solution is the $34 or $3,400 that we made in profit, right? So if we exceed 5.7, then our optimal profit is no longer $3,400. It'll be different. Okay? And of course we can decrease it as much as we want because that's not a problem. Decreasing our profit margin is not going to change it, right? Now over here we have a reduced cost of 4. Our current profit margin is $400. So we have to increase it by 4 to $800 in order to make any snow fence. All right? And if we increase it beyond 4, like even if we increase it to 4.1, that's going to change the objective solution. It's going to change from 3,400. And we don't know what that change is going to be. All right? So that is what this information is telling you. With the constraints, we remember that we had these two that were the binding constraints, right? So we go over here and we see, oh, there's a shadow price over there. What does that shadow price mean? That shadow price means that when I increase my resources for the Y machine by 1, in other words, if I add another 100 hours of Y machine time, then I'm going to increase my profit by 4. In other words, by $400. Okay? So that's really valuable information, right? I can increase my profit by $400 by adding 1 more hour of 100 more hours of machine time. So now I can see what's the trade-off. Does it make sense? Similarly, I can add 1 more hour or 100 more hours of loom time, and my profit will increase by $100. Okay? So that is, and we can check all of these things. We can go back to the thing, to the sheet, and we can check. So remember I said my shadow price, my allowable, my reduced cost was 5.7. So if I increase this to 9.5, that should keep the objective function the same, but I should now start manufacturing some roofing mesh. So let's solve it and see. You can change that and solve it and see what the solution is. So this is not changed, but now I've started making some roofing mesh. Okay? So now this is entered into the problem. And I can do the same thing for this as well, and you'll see that now I'm making snow fence. Okay? So let's go back to the original, and I have a shadow price over here of, what is the shadow price? For the Y machine of 4. That means if I add 100 hours, so if I increase this to 7, then I should now increase my profit margin from 3,400 to 3,800. So now my profit margin has gone up from 34 to 38. Okay? So that's the shadow price. And you can do the same thing for the other one, and it'll go up by 100. Okay? And the allowable increase and decrease is the same thing. So that's basically what the sensitivity report tells you to do. Now there are a couple of things. I'm not going to get into the details of this, so for the purpose of this class, this is really general knowledge. What you need to know is what information is available just for general knowledge purposes. All right? Because as you saw, I only changed one thing at a time. Now that's not the way it should be done. You can change multiple inputs because obviously we want to find out how we can make all of these. But just to show you the math behind that, it's going to take me probably another 3 or 4 lectures, and for that we probably need to have a dedicated semester just for doing linear programming. Okay, so let's not get into that, but I just wanted to show you the power of linear programming. Okay, so that when you do the network programming, you can actually see where all of this information is coming from to help you understand and make decisions about, okay, where do I locate my warehouses, where do I locate my inventories, which transportation carrier should I use, etc. So that's the power of linear programming. Any questions? Okay, so all of the class problems are listed here. I strongly urge you, short of requiring you, which I can't, because you all have your own free will, but I strongly urge you to go in and look at each one of the problems, look at how they're constructed, and make sure you understand what that is. Okay? All right? Okay. So, coming back to our heuristic solution. Anybody solve this by heuristic? Can anybody give me a good heuristic for this? I know a couple of you came to my office and I gave you some tips, right? So you want to share what you've done? How do we solve this problem using the heuristic method? Nobody? Looks like this is a good candidate for an exam question then, right? Hassan.
Should we start? I will start with the warehouse with the 200. I'm going to supply.
Why did you start with the warehouse at 200? First, tell me what heuristic you're using.
Trying to find the best, easy way from the warehouse to the customer, cheap, lower the cost.
Best, easy, good for customer, cheap. Choose. There's 4 criteria. Which one are you choosing?
Cheap.
Cheap.
Lowest cost.
Lowest cost. Excellent. Tell me. So what is your criteria for, what's your heuristic now? It's the cheapest, right?
As I think so. It's not 100% sure.
It should be a rule. It should be a rule. It doesn't matter if you're 100% sure or not. I can also, the same rule, I can also use ship on the most expensive route first. Yes, Eric.
So what do you ship? All, so 200 warehouse was 2, and 300 was 1, warehouse 1, 2.
I can't hear you, Eric. I'm sorry.
So would you send all 150 units to customer A from 200
Why?
because that's the cheapest route possible?
Okay, so tell me the heuristic that you're using.
Well, I'm using the cheapest model.
Okay, so excellent. So I wanted you to think about it yourself first, and then tell you that there is a class of heuristics called greedy heuristics. And we're doing a second example again. I want you to think about that. Greedy heuristics tries to minimize your costs as much as possible. So what you all are saying very intuitively is we are being greedy to send as much as we can on the next cheapest lane first, right?
Maybe what I'm trying, he's doing and I'm doing the same time.
Same thing, exactly.
With the warehouse, so we have 200, and that's
Yeah.
the cheapest way to the customer one would be 7 parts, and we could deliver 150, and we have 50 left.
Yep. So we have. So that's the heuristic, the cheapest lane next. So I sent 150 items to fulfill customer A's demand. What's the next cheapest route? This one. Okay. So I now cancel out 8 because we already satisfied that customer demand, right? So what's the next cheapest route?
I think warehouse one to
No. When you use a heuristic, you just use the heuristic, all right? Then afterwards we come back and then we see how we can improve upon it. Yes?
And the last 50 is second customer.
So the next cheapest route is 9. Okay? So this cheapest route is no longer feasible because we already satisfied all that customer demand. The next cheapest route is 9. So now we've got nothing left. We send 9 items here. We got 50 left. What's the next cheapest? 10, right? So we have 250 left. We send 50 here. We cancel out that customer demand. Now we only have one option. We have 11 or 12. Obviously we're going to choose 11, right? So we have 50 left over here. We have 200 times 11. And we finish that customer demand. Now we just add up all this 9 times, so 450, and then 450, 1050, so 1500, 1500, and 500, 2000, 2000, and this is so 4600 or something. It's 4400. All right, so that's the total cost. And the solution is 50 items on this lane, 150 items on that lane, 50 items on that lane, and yeah, that's it. So that's the solution. And then we can go in, put it into the optimal, put it into solver and see if it's right? Any questions about this heuristic? It's called a greedy heuristic. It's called the cheapest lane next. Okay? So whatever the cheapest lane is, we ship on that next. Yeah? Now we can go in and say, okay, how can we improve this? You know, and then we go in and see what improvements we want to make after the fact, not before the fact. Okay. So let's do another quick heuristic, just so that you understand how it can be applied in different circumstances. Here's our production inventory problem. I'm not going to solve the problem. You solve the problem for your homework, and there is a problem on the homework as well. Here, what is a greedy heuristic you'd use over here? Should be pretty quick by now. A greedy heuristic? Yes, Bradford.
We just need to make 300 in week 1 to save money.
Yeah, you just make 600 rather in week 1, right? And then figure out, you know, can we, because you're going to satisfy all demand and see if it makes sense or not, right? And then you can go back, yes?
300 and week 1, 303.
Yeah, you could do that as well. So you compare the two and you'll see what the answer was. So that's your greedy heuristic, okay? It's as simple as that. And then you multiply all the numbers, you look at how much you produced when, how much you had in inventory, and that's it. Any questions? So now you know how to solve problems using heuristics, and now you know how to solve problems using a linear program. So now we're going to start doing some really good, interesting, involved stuff in inventory management, routing, and facility location network design, where you'll get to apply all of these things, right? Okay. So let's get back to our current day's lecture. Any questions, by the way, on any of the stuff that we've covered today so far? Yes,
Can you
George.
go back one slide so I can see the greedy heuristic? Start down the line.
This one?
Yeah.
I also solved it. I think I solved it. And you can see the lecture as well. Tell me when you're done, because I want to start today's lecture. As I keep reiterating, when I solve the problem, it is very intuitive and easy for you to understand. But without the solution and without a mental model of how to approach a solution, it becomes exceedingly hard. The only way you can get from where you are right now to being proficient in this is by practicing. Okay? So do the practice problems. I promise you by this weekend I will have the practice solutions up. I will try to have a video up as well, so that you can see how the solutions are made. And that way you can go ahead and also get a second introduction, so to speak, to a linear programming. Done? All right. So today we're going to talk about binary programming. Okay. So with binary programming, we're introducing a new variable, which is a special variable. It can take on binary values, which our friends in MIS know means 1 or 0, right? Good. So we're going to learn how to write them, interpret them, and then you already know how to solve them. So, binary variables are extremely useful when you want to introduce a variety of different logic in your problems. Okay? So you have some sort of if-then case, or you want to say if this happens, then that happens. Or you want to create a scenario where if I incur a certain cost, then I build a certain warehouse. Or if I build a certain warehouse, then I also incur this cost, a fixed cost. So it's extremely powerful in that case. We also have scenarios where we can force things to happen, again, because of the if-then solution, or if-then the if-then logic of these binary variables. If I'm going to build a warehouse here, then I'm going to force transportation on these lanes. Okay, and we'll see how these all work. So, there's going to be 3 cases I'm going to show you. All right? Most of the cases will be covered by those 3 cases. Or all of the cases, I should say. Here, we want to choose one location out of many. Remember that problem I showed you at the beginning of solution methods in linear programming? We have 60 locations and we have to locate 15 warehouses. Took us almost 1800 years to solve that problem. We did it by enumeration. So here we can solve this problem in a few milliseconds. So we have 4 different locations and we need to find out one where we want to locate our warehouse, right? So what we do is, now it's a decision that we have to make, right? So there's a decision variable involved. So the decision variable is where. We have 4 wheres, we want to choose one of them. So all we have to do is set the decision variable where y1 is equal to 1 if we locate in this spot, 2 if we locate in Ohio, 3 if we locate in Utah, and 4 if we locate in Idaho. So we have the binary 1, and then 0 if we don't locate in that particular location. Does that make sense? Okay. Now, once we've done that, it's very simple to set up a constraint where we say, we add up all these y's, and we say, we want to be equal to 1. That means the problem can only select one location. Yeah? So, what if we could choose at the most 2 locations? So what's another way to say this? I was actually doing this with my son yesterday. So what's another way of saying, what if we could choose at most 2 locations? Or how would we represent that using a mathematical formulation like this? Yes, sir?
y1 plus y2 plus y3 plus y4 is 0.
Okay. So Andy is saying, okay, let me just take this out. So in other words, you're just saying that we set is equal to 2, right? Who agrees with that? Who doesn't agree with that? Okay, why?
There's no 2 in binary.
This doesn't have to be binary. I can set this equal to 15 as well. So I can have 300 variables over here, or 60 variables, and say I want to choose only 15. Right? So these have to be binary. Okay? Why do you say no? Why do you disagree?
Right. Well, it says at most 2 locations, so that means that you can still have just one location. So I would say less than or equal to 1.
Excellent. Less than or equal to Andy. All right? And all of you else, everybody else who was confused, because at the most 2 locations means a maximum of 2 locations, right? Okay? But is that all? So I can say y1 plus y2 plus y3 plus y4 is less than or equal to 2. Right? Everybody agree with that? How many says this is right? How many says this is wrong? Why are you saying it's wrong?
I'm not sure why. I just don't think
Sorry?
I'm not sure why. I just don't think it is right.
Okay. Eric?
I mean, having it less than or equal to 2, isn't that, is it 2 or 1? Or has to be 0, we just can't add.
Yeah, it could be 0, right? Because we could set, the program can set all of these equal to 0. It's a minimization of cost. We just not open any warehouse, right? So what do we need to do to prevent that from happening?
You say all registers is set 0.
Sorry?
All registers is set 0.
That's a restriction. These are already restricted to 0 and 1. How about if we said y1 plus y2 plus y3 plus y4 is greater than or equal to 1, right? And we have 2 constraints. Yeah? So now this constraint will ensure that it's at least 1. This constraint will ensure it's a maximum of 2. So even though I have just one statement, I can have more constraints resulting from that one statement, right? Because of the conditions implied. Now I can give you one statement and you have to write maybe 6 constraints to satisfy that one statement, right? So think about all of the mathematical conditions that need to be satisfied and how the constraints can be used to satisfy that. Does that make sense? And again, through your homework, you'll see some more examples of that. Okay. So our next example is modeling fixed costs. So here, if we locate in Idaho, we incur a fixed cost of $300,000. So we say y4 is equal to 1 if we locate in Idaho, and y4 is equal to 0 if we don't locate in Idaho. And then the objective function, we have all these variable costs, all our transportation costs, and all we do is we just add this to the objective function. So in the objective function, all we're doing is we're adding this fixed cost. So if y4 is located in Idaho, or if we locate in Idaho, y4 is equal to 1, and this fixed cost $300,000 will be added to the objective function. Right? And then we have our last condition where we have dependent decisions. And here there's a variety of different dependent decisions. For example, I can say if we open a warehouse in New York, then we have to open a warehouse in Chicago. And you'll see that in your homework. Or if we're going to ship to customer A, then we have to ensure that we ship 600,000 units. In other words, a truckload capacity. Okay? If we're shipping to customer B, we have to ensure that we ship at least 500 units. That's a less than truckload capacity. So all of these dependent decisions can be modeled, and here's just one example of them.
What's the meaning behind O dash or O for?
So this is y4 is equal to 0, and this means otherwise. Okay? There's all kinds of short forms we use in math because it tends to get really big. So you use short forms just to make things digestible. Okay, so what is going on here? So if we locate a warehouse in Idaho, it's equal to 1. If not, it's equal to 0, right? That much we know. But if we locate in Idaho, then there will be lanes on which we can transport freight from the warehouse in Idaho to the customers, right? So say there's a lane X4. Okay? So this constraint is called a forcing constraint. Is X4 has to be less than or equal to some large number C. Often it's the capacity of the warehouse in Idaho. Okay? So this large number C times Y4. Now what happens over here if we don't select Idaho as a location for a warehouse? Y4 is equal to 0. This becomes 0. And then this is forced to be equal to 0. Everybody see that? Yeah? But if y4 is equal to 1, then we are forced to ship, we can ship anything from 0 all the way up to the maximum capacity C. You see that? Anybody still confused with this? Okay, so what do you not understand yet? Here, we have C is some large number. It's a real number. We're just using C over there, and you'll see in the next example. C is just representing a large number. Okay, it could be infinity. We put infinity over here. It doesn't matter. But usually we use the capacity of the warehouse 4. So what we're doing is we're multiplying this large number by y4, and if y4 takes on a value of 0, then this right-hand side becomes 0, right? So if the formulation, if the mathematical formula, mathematical program here sets y4 equal to 0, then there's going to be nothing here on the right-hand side. Yes?
So you're multiplying the C and the y4.
Yes. So it's C times y4, okay? And then x4 is forced to be 0 because the right-hand side is 0. But if y4 is equal to 1, then x4 can take on any value from 0 all the way up to the full, whatever that large number is. We set it equal to infinity to infinity. Okay? And in the next example, you'll see how that works. Did I answer your question? All right. So let's take a look at an example. This is exactly like your transportation example, the one we just solved using heuristic, except that it's got 3 warehouses now instead of 3, instead of 2. So everything is the same. We just change some units here and there. And now what we want to do is we want to incur a fixed cost, or we are saying we're going to incur a fixed cost of $100,000 each time we ship out of a warehouse. In other words, we're trying to figure out where to locate the warehouses, and when we locate a warehouse, we have to open a warehouse, and the fixed cost for opening the warehouse is $100,000. Yeah? So what do we know? We want to set our yi is equal to 1 if we use warehouse I, and it's 0 otherwise. So for each of our warehouses, we are going to set one binary variable, and that binary variable is called y sub I, and we set that equal to 1 if we open a warehouse at location I. Otherwise, we set that equal to 0. So, in terms of the formulation, it's pretty straightforward. Like I showed you in part B, in the B example, all we're doing is we have everybody should be familiar with how we got this right now. Everybody is okay with that? Yeah? With the variable cost of shipping? To that objective function, we're just adding the fixed cost. So 100,000 times y1 plus y2 plus y3. Yeah? Are we okay? If you're not okay, just put up your hand and we'll go over any area that you want me to go over. All right, so everybody's comfortable with the objective function? All right, so here we have the warehouse constraints. We have 3 warehouse constraints. Their capacities are 50, 275, and 275. And you can see we have warehouse 1, warehouse 2, and warehouse 3. They're shipping to customer 1, 2, and 3. So these are just the lanes, right? The amount coming out of the warehouse has to be less than the capacity, less than equal to the capacity of those warehouses. Here on the right-hand side, we've got the customer constraints. So we've got customer 1, so the J values now are changing, 2 and 3, and they're coming from warehouse 1, 2, and 3, 1, 2, and 3. And we have to meet the demand of 100, 250, and 150. So those are customer constraints. Now here what we have are the forcing constraints. So these forcing constraints are where we have, for lane 1, we ship on lane 1, we ship on lane 1, going from warehouse 1 to customer 1, only if warehouse 1 is open. We ship from warehouse 1 to customer 2, only if warehouse 1 is open. And we ship from warehouse 1 to customer 3, only if warehouse 1 is open. Yeah? So now what am I using here? I'm using a large number, 500. So why did I choose 500? I chose 500 because when you add up the total customer demand, it adds up to 500. I could also put infinity over here. Doesn't matter what I put over here. It has to be greater than 500. Okay? Is everybody cool with that? Okay. So that's the first part of the formulation. Now there's no other parts, but I can actually look at this here, and I can actually combine all of these forcing constraints. Right now I've got 9 forcing constraints, but I can combine them and make it a lot shorter. So anybody, any ideas how you can combine these constraints?
Add them together.
How do you add them together? Good.
S11, S12, S13,
Excellent. Excellent. Because see, the right-hand sides are all the same, right? So this right-hand side is all the same. So we use S11 plus S12 plus S13 is less than or equal to 501. And you do the same thing for the other two. So that's what we're going to do. S11 plus S12 plus S13 is less than or equal to 500 Y1, and so on. Yes, Eric.
What if, like how it says S11, S12, and S13 separately, right?
Yes.
How they're all less than or equal to 500. If they're all equal to 500, they're technically equal, but counted and all out.
Correct. So, very good observation. So this is saying less than or equal to 500, right? But when you add all of these things up over here, this is forcing it to be less than or equal to 50. What's that? No. So somewhere in the problem, there has to be an expression that's limiting how much those variables can, what values they can take on. Good. Good question. Yes?
Can I do them differentiate? Like S11, S21, S31 equal to 500?
S11, S21, and S31 is equal to 500?
Yeah.
No. Because what you're doing is you're saying that you're changing this customer demand to 500 when this customer demand is 100. Okay? Okay. Now, what are these basically? S11, S12, S13. What is this? This is the left-hand side of the warehouse constraints, right? And what did I start off by saying about that C? You usually said C equals to the capacity of the warehouse, right? So how can I reduce this even further and make this formulation even smaller? Do you agree with me that S11, S12, and S13 is exactly that? Yeah? Similarly for these two, those are the left-hand side. Yes, Jake?
Guess I'll take a shot.
Sure.
X1 less than or equal to 500 times Y1.
So we already moved past the 500. We don't need 500 anymore because we've combined them. So I'm giving you a clue by writing out the left-hand side in place of the warehouse constraints. So the only thing that we need are the right-hand side of the warehouse constraints. So how would we modify the warehouse constraints to include the forcing constraint as well?
We just add equal or less to 100 for the first one.
What is the capacity? 50, right, for the first one? The warehouse capacity for the first one is 50 units. Like I said, when I give it to you, it's going to sound so easy. So what's the expression? Let's start there. What expression should we use? Less than or equal to? Has to be less than or equal to, right? Because it's a warehouse.
Should be less than equal to 59.
Okay, so 50. But how do we include the forcing constraint? Right, here we have the forcing constraint there, right? 500 y1, 500 y2, 500 y3. So what do we do here? 50 y1, 275 y2, and 275 y3. So now, this original warehouse constraint becomes a forcing constraint just by multiplying the right-hand side by y1, y2, and y3. Yeah? So now they both act as a capacity constraint as well as the forcing constraint. Yes, sir. So 50 times y1, 275 times y2, and 275 times y3. So I'm multiplying those two. All right? y1, y2, and y3 is are binary variables where if we locate at y1, if we locate at location 1, then y1 is equal to 0. Otherwise, it's y1 is equal to 1. Otherwise, it's 0. If we locate at y2, if we locate at location 2, y2 is equal to 1. Otherwise, it's 0. And similarly for 3, we locate at location 3, y3 is equal to 1. Otherwise, it's 0. Exactly. That's just on or switch, just like a binary, any binary variable is supposed to. Yeah. So I'm switching it off if you're not locating there. So none of these lanes can take on any values other than 0. Okay. Do you understand at least the concept of what we did so far? Yeah. All right. Let's move on to the next one. So we want to decide that a retailer, so we want to improve our customer service. So how do we improve our customer service? By ensuring that our warehouse builds a relationship with, or the customer works only with one warehouse. So they develop a relationship with that warehouse. So that warehouse knows that customer well. So one way we do that is we do single source, we do single sourcing. So we say, okay, warehouse A, you're only going to serve, or customer A only going to be served by one warehouse. Okay, customer B also only going to be served by one warehouse. So the question is, how do we now define decision variables and then write constraints to ensure that we make this happen? So the decision now is, what's the decision that we have to make? A customer can only be served by one warehouse, right? So which warehouse is going to serve which customer? Yeah? That's a decision we have to make. So we add these binary variables. Yij is equal to 1 if warehouse I serves customer J. And then you can say 0 otherwise. Now, once we have these constraints, it becomes relatively simple. Once we have these decision variables, it becomes relatively simple to actually add the constraints that we want. Now all we have to do is we have to set the sum of the variables of the lanes going from each customer to all three warehouses equal to 1, right? So how many lanes are going to a customer? 3. A lane is going from warehouse A, or warehouse 1, warehouse 2, and warehouse 3, right? So we take the sum of those 3 variables for that one customer and we set it equal to 1. So we say y1, 1 plus y2, 1 plus y3, 1 is equal to 1. So customer 1 from warehouse 1, customer 1 from warehouse 2, and customer 1 from warehouse 3, the sum of all of these has to be equal to 1. Yeah? Does that make sense? So can somebody give me the other 2 customers? Sorry? Somebody want to do it? Yeah. Go ahead. Yeah. And then you have y13 plus y23 plus y33 is equal to 1. So now, of the warehouses serving that customer, only one is going to be chosen to serve each customer. And then, of course, for our actual lane, how much we're shipping on each lane for those lane variables, we have to set a constraint where we say less than or equal to 500 times yij. Now here what happens is if we do not ship on one of these 9 lanes, then that decision variable is going to be equal to 0. So this right-hand side turns to 0, and then this shipping variable automatically turns to 0. Yes?
6, 5,
Sij. So that's Sij is the shipping variable that we use in the big program, right? So now these are just extensions that we're adding on to our program. So an example would be if we took S32 less than or equal to 500 times Y32. So in other words, if warehouse 3 doesn't serve customer 2, this will be equal to 0. So the amount we ship from warehouse 3 to customer 2 is going to be equal to 0. Yeah? As an example, for the shipping variable of how much we ship from warehouse 3 to customer 2, if from these constraints we do not ship anything from warehouse 3 to customer 2, if this becomes 0, then this will be set to 0 in the program. This right-hand side is equal to 0, and so the amount you ship is also going to be forced to be equal to 0. Yeah? All right? Okay, good. Let's move on to some of these other extensions. So in this example now, we have a fixed setup cost of $50 at the beginning of each period. So in other words, if we produce in that week, we're going to incur a $50 production cost, $50 fixed cost for producing in that week. So what's the decision variables that we are going to have over here? What's the binary decision variables we're going to have over here? It's a binary variable. It can take on a value of 1 or 0. In other words, it's a question of yes or no. Yes?
Since we want to produce that week 1.
Exactly. If we produce in week 1. So y1 is equal to 1 if we produce in week 1. and all of these will be 0 otherwise. So for each of the weeks, you set up a binary variable equal to 1 if you produce in that week, and 0 otherwise. And now, we have our same objective function here. We have the fixed cost that we add 50 times y1, 50 times y2, 50 times y3. And now there's a forcing constraint where if we produce in week 1, then our P1 will take on a value of anywhere from 0 up to 600. And same way for week 2 and also for week 3. So everything else remains the same, and then we add just these forcing variables where we produce in that week only, or we incur an amount of production only if we produce in that week. And then we add these variables y1, y2, and y3. And this is another way of mathematically saying that these are binary variables, belongs to the set of 0 or 1. Yeah? Any questions about this? And then we have a whole bunch of other problems that we could solve. I just want to share some with you. Some really interesting problems. This is, for example, a lot sizing problem. And we can use this in a warehouse. We could use this for production. Here we are saying that we can ship from a warehouse between 20,000 and 40,000 grams. So why can't we just say that? We can say x1 is less than equal to x1 is greater than equal to 20,000, and then 40,000 is less. X1 is less than equal to 40,000. So that gives us a constraint where we're forcing x1 to be less than 40,000 and greater than 20,000. But what happens if we are shipping on a certain day, and on that day the warehouse is either open or closed? Okay, so we look at a week and we want to schedule our shipments for a week, and we want to see on which day of the week we want to keep the warehouse open, depending upon whether we want to staff it or not. And now we can say if we want to ship on day 1, we have a binary variable to say it's equal to 0. 1 if we ship, 0 otherwise. And the next one is the amount of pounds that we ship. So now we're just multiplying the maximum and minimum value of the shipments by whether the warehouse is open on a particular day or not. And you could do this for production scheduling as well. You could do this for transportation scheduling as well. Another really cool problem is the knapsack problem. So here we have a variety of different items, and it's usually used for loading transportation equipment. It can also be used for, and we'll actually be using this for scheduling when we do the transportation scheduling problem, so I'm not going to spend too much time on it. But here we have items that have a variety of different attributes. So say you have a knapsack and you have a whole bunch of different things you want to take with you on your trek. Okay? Each of those items have a volume and a weight. You can only lift a certain maximum weight, and your knapsack can only carry a certain volume. So you can set binary variables for each of those items, and based upon the volume weight constraint and then the value that you ascribe to it. For example, you could put some value from 1 to 100 for food, for medicine, for water. So certain will have a maximum value, and you want to maximize your value within the constraints of your knapsack. You can also use this to if you're into fantasy sports of any kind, basketball, football, now the NCAA March Madness is coming up, we can set up a problem like this. I had no idea about basketball. I won my pool all the time at Ohio State because I just used a program like this. And it is relatively simple to set this up if you have all the input data. And here, each player is a binary variable, and you want to select that, or in this case, each team is a binary variable. You want to select that team or not, right? And find out which team will eventually win. So you set up a game, and then you can run a linear program, or for fantasy football, you have a whole league of teams, and you want to find out which, or have a whole league of players, you want to find out which is the best player to put into each position for your team, and that's a binary variable. So you have a whole host of really cool problems you can solve using this. All right. So I said that you cannot have any decision variables on the right-hand side. So a very simple modification, you just use simple algebra and add both sides by 20 times y1, and you transform the equation into that.
So the point is just like an example.
Sorry? Yeah, this is just an example. So for our 500y1, for 500y11, it would be x11 or s11 minus 500 times y11 is less than or equal to 0. And the thing to remember is, in our Tableau, you're going to have column headers for all your S11 variables, all your regular variables, and you're also going to have columns now for your binary variables. And you will set in the drop-down box, remember I showed you, there's a bin, so you're going to set those changing variables to bin. Look at the Excel solver sheet and see how I've solved these, the slick oil problem. See how I've set that up so you understand how to do it. All right? All right, have a good weekend. I'll see you next week.
We're going to be here on